Imagine an aircraft so advanced it doesn't need a pilot, so stealthy it vanishes from radar, and so autonomous it refuels itself mid-air without human intervention. This isn't science fiction, it's the X-47B. In April 2015, this groundbreaking drone made aviation history, completing the first fully autonomous aerial refueling and showcasing technology that seemed decades ahead of its time. With a wingspan rivaling a fighter jet, unmatched stealth, and capabilities pushing the boundaries of unmanned systems, the X-47B has redefined what's possible in military aviation. But as we celebrate this marvel of engineering, a controversial question demands our attention. Is the X-47B a beacon of innovation, or a chilling preview of a future dominated by autonomous warfare? Revolutionary design features of the X-47B. The X-47B represents a significant advancement in aircraft design, specifically through its innovative flying wing configuration. The aircraft features a defined triangular shape with no vertical surfaces, making it a true flying wing design similar to the B-2 Spirit bomber. The flying wing configuration represents a unique and innovative approach to aircraft design, seamlessly blending the fuselage and wing into a single, unified structure. In this design, all components, including onboard systems and payloads, are integrated within the wing itself, creating a streamlined and efficient layout. This configuration offers a range of compelling advantages. By utilizing the entire structure to generate lift, the design significantly enhances aerodynamic efficiency. The absence of a traditional fuselage reduces overall weight, leading to lower fuel consumption and extended operational range. Additionally, the smooth, continuous surfaces of the flying wing minimize radar reflections, making it an ideal choice for stealth applications. However, this design also introduces challenges. The lack of vertical and horizontal stabilizers critical for traditional aircraft stability necessitates the use of advanced, computer-controlled flight systems to ensure precise handling and maintain aerodynamic balance. These sophisticated systems underscore the technological complexity required to harness the full potential of the flying wing configuration. The X-47B utilizes cutting-edge stealth technology by incorporating specialized radar-absorbing materials into its design. These materials effectively reduce its radar signature through two key mechanisms. First, they absorb electromagnetic waves by leveraging dielectric and magnetic losses, converting the energy into heat and minimizing reflection. Second, they create multiple internal reflections of incident radar waves, dispersing the energy and further diminishing the aircraft's detectability. The aircraft surface incorporates carbon-based materials, specifically chosen for their exceptional properties, including high electrical conductivity and stability under harsh conditions. These materials are optimized through careful adjustment of their composition, microstructure, and surface geometry. Specifically designed for carrier operations, the X-47B features an innovative wing folding mechanism that reduces its wingspan to 30.9 feet when folded. This engineering solution addresses the space constraints on aircraft carriers while maintaining the drone's combat effectiveness. The aircraft is equipped with a range of design features specifically tailored for carrier-based operations. To endure the harsh maritime environment, it incorporates corrosion-resistant materials that ensure durability and longevity. Its reinforced undercarriage, combined with an arrestor hook, allows for secure landings on carrier decks. Additionally, an automated folding mechanism optimizes space efficiency, enabling seamless integration into the limited confines of naval flight decks and hangars. During carrier operations, the X-47B has demonstrated its ability to seamlessly integrate with conventional carrier assets, specifically in demanding deck environments. The folding wing system allows for a quick transition between flight and storage configurations, consequently optimizing carrier deck space utilization. Advanced propulsion systems. At the heart of the X-47B's impressive performance lies the Pratt & Whitney F100PU220U engine, a power plant that exemplifies advanced aerospace engineering. This non-afterburning variant of the proven F100 family serves as the cornerstone of the aircraft's propulsion system. The F100PU220U delivers remarkable performance metrics with up to 16,000 pounds of thrust. The engine's physical dimensions are noteworthy: length 191 inches, inlet diameter 34.8 inches, weight 3,826 pounds, thrust vectoring capabilities. The engine incorporates sophisticated modifications for carrier operations. A significant adaptation involves replacing the standard F100-220 thrust bearing with a higher strength component from the F100-229, therefore ensuring resilience during high-G launches and hard landings. Moreover, the engine features a unique exhaust system that converts the traditional round outlet into an oval shape, accordingly matching the aircraft's stealth requirements. The F100-220U demonstrates exceptional operational flexibility through several innovative features. The engine operates effectively with both J-8 and the Navy's JAP-5 fuel, hence providing versatile deployment options. Similarly, the propulsion system supports autonomous aerial refueling capabilities, which significantly extends the aircraft's operational range of 2,400 miles. The engine's integration with the X-47B's autonomous systems required innovative solutions. An engine interface unit acts as a translator between the aircraft's autonomous flight control system and the engine's digital control system. This sophisticated interface enables seamless communication, therefore maintaining optimal performance during all flight phases. Throughout extensive testing, the engine has demonstrated remarkable reliability. The program included more than 50 flights on Air Vehicle 1 and approximately 30 on Air Vehicle 2, with the engine performing flawlessly throughout these trials. The propulsion system underwent accelerated mission testing to validate its durability and performance in maritime environments. The engine's heritage stems from over 12 million hours of operational experience gained through its predecessors in the F100 family. This mature technology base, paired with components common to modern F100-229 and F135 engine technologies, enables risk development and increased fleet commonality. Autonomous flight control systems. The autonomous flight control system of the X-47B stands as a testament to advanced aviation technology, enabling operations without direct human intervention. This sophisticated system orchestrates complex flight maneuvers through a combination of cutting-edge algorithms and sensor arrays. The X-47B relies on advanced decision-making algorithms to manage flight operations with precision and autonomy. Initially developed to meet the demanding requirements of carrier-based operations, its computer-controlled system processes real-time data to execute intricate maneuvers with exceptional accuracy. This capability has been demonstrated in tasks such as autonomous carrier deck operations, touch-and-go landings, heavyweight landing procedures, and complex pattern turns and approaches. The aircraft's navigation and positioning technology further enhance its operational effectiveness. Utilizing a hybrid GPS and vision-based architecture in conjunction with Honeywell's state-of-the-art navigation systems, the X-47B achieves precise positioning critical for its missions. This technology enables accurate autonomous approaches during carrier landings, precise aerial refueling maneuvers, and stable position maintenance in high-stakes operations. During aerial refueling, the X-47B communicates seamlessly with a government-designed refueling interface system aboard tanker aircraft, ensuring smooth coordination and flawless execution of this complex procedure. The aircraft incorporates comprehensive safety measures for autonomous operations. Although operating independently, the system maintains constant communication with the carrier environment. The emergency protocols include automated wave-off functions for aborted landings, safe separation procedures during refueling, and rapid response capabilities for unexpected situations. The system has proven its reliability through extensive testing, completing 26 deck touchdowns, including 21 precise touch and goes and 5 arrested landings. Subsequently, the aircraft demonstrated its capability to operate alongside manned aircraft, performing launches and recoveries at 90-second intervals. Primarily designed for carrier operations, the system translates visual cues into unambiguous digital instructions, ensuring precise communication between the aircraft and ship. The X-47B's autonomous capabilities extend beyond basic flight operations, as evidenced by its successful completion of the first autonomous aerial refueling in April 2015. The system's sophistication allows it to adapt to various operational scenarios, utilizing onboard sensors for real-time decision-making. This adaptability proves essential in contested environments where the system must operate effectively even under GPS or communications jamming conditions. Carrier integration engineering. Integrating unmanned aircraft into carrier operations marks a groundbreaking achievement in naval aviation history. The X-47B drone pioneered this advancement through extensive testing and demonstrations aboard various aircraft carriers. The launch and recovery systems of the U.S. Navy's X-47B drone marked a historic milestone in 2013, as it became the first unmanned autonomous aircraft to complete carrier-based launches and recoveries. This achievement was the culmination of an extensive testing process that began with initial shore-based catapult trials at Naval Air Station Pageant River. The system then advanced to carrier qualification testing aboard the USS Harry S. Truman, followed by its first autonomous carrier landing on the USS George H.W. Bush. Subsequent testing focused on advanced integration with manned aircraft, showcasing the drone's ability to operate seamlessly in a complex carrier environment. The X-47B demonstrated extraordinary precision during these operations, executing 7 autonomous carrier landings with an impressive accuracy of touching down within just 7 seconds of its target. The Northrop Grumman X-47B introduced innovative deck handling capabilities through its control display unit. This arm-mounted remote control system enables operators to control engine thrust and braking, execute precise turns using nose-wheel steering, maneuver the aircraft into catapult position, and guide the vehicle out of landing areas. Primarily, deck operators work in coordination with flight deck directors, translating traditional hand signals into wireless commands for the aircraft. The system demonstrated exceptional reliability through multiple deck handling trials, particularly during nighttime operations. The X-47B's integration into carrier operations is supported by a highly advanced digital communications infrastructure. This system enables seamless interaction between the aircraft and carrier personnel throughout launching, recovery, and flight operations. Key aspects of this infrastructure include a fully digitized carrier-controlled environment, real-time data exchange capabilities, compatibility with existing carrier systems, and automated response protocols. The U.S. stealth drone completed extensive testing aboard USS Theodore Roosevelt, performing multiple arrested landings and catapult launches while maintaining 90-second intervals between operations. This achievement validated the aircraft's ability to operate efficiently within standard carrier procedures. The X-47B's performance metrics underscore its successful integration into carrier operations. The aircraft completed 8 catapult launches, 30 touch-and-goes, and 7 arrested landings across various carrier vessels. These accomplishments essentially proved the viability of unmanned systems in carrier-based operations, setting new standards for future naval aviation developments. Stealth technology implementation. Stealth capabilities form the cornerstone of the X-47B's combat effectiveness. The U.S. stealth drone incorporates multiple layers of radar evading technologies, making it a formidable asset in contested airspace. The X-47B incorporates advanced design principles to significantly reduce its radar cross-section, enhancing its stealth capabilities and making it difficult to detect using conventional radar systems. A key element of this stealth is the elimination of corner reflectors, which are common sources of strong radar returns. Additionally, the aircraft features precisely angled surfaces that deflect radar waves away from their source, effectively scattering signals and reducing their visibility. To further enhance its low observability, critical components that could produce strong radar reflections are strategically shielded, while parallel edge alignment minimizes radar spikes by preventing the concentration of radar returns. One of the most notable features of the X-47B's stealth design is the use of S-shaped inlets and exhaust ducts, which conceal the engine's reflective surfaces from radar exposure. This sophisticated design was developed through detailed electromagnetic scattering analysis, leveraging radar imaging technology to identify and mitigate primary scattering sources. This iterative design process ensured that the X-47B achieved an exceptionally low radar signature, essential for modern combat scenarios. In addition to its radar cross-section reduction, the X-47B employs cutting-edge infrared signature management systems to further enhance its stealth. By integrating multiple sensor technologies, including electro-optics, infrared sensors, synthetic aperture radar, and maritime moving target indicator systems, the aircraft achieves superior thermal concealment. These systems work cohesively to manage and minimize the heat generated by the aircraft during operation, a critical factor in evading IR-based detection systems. Sophisticated heat management techniques, combined with specialized surface treatments, effectively reduce the X-47B's thermal signature, allowing it to remain undetected even in scenarios where adversaries rely on advanced IR tracking technologies. Through this dual approach of radar and infrared signature management, the X-47B stands as a benchmark in stealth technology. The electronic emissions control system is a vital element of the X-47B stealth design, enhancing its ability to operate undetected in hostile environments. At the core of this system are advanced electronic support measures, which work in conjunction with other cutting-edge technologies. These include a ground moving target indicator for identifying and tracking moving objects on the surface, an inverse synthetic aperture radar for detailed imaging and reconnaissance, and an advanced communications system for secure and efficient data exchange. Surface treatment plays a crucial role in the overall stealth strategy. The aircraft employs specialized coatings that absorb radar waves rather than reflect them. Nevertheless, these materials require regular maintenance and inspection to maintain their effectiveness. The stealth enhancement design follows a systematic approach regardless of the operational environment. This methodology includes precise assessment of electromagnetic scattering characteristics and identification of primary scattering sources. The design team utilized advanced optimization techniques, namely the Kriging surrogate model, to evaluate both aerodynamic and stealth characteristics simultaneously. The X-47B's stealth capabilities extend beyond basic radar avoidance. The aircraft demonstrates remarkable effectiveness in penetrating protected airspace, making it particularly suitable for high-risk strike missions. Through careful integration of shape design, materials, and electronic systems, the X-47B achieves a low observable profile that enables it to operate effectively in contested environments. Mission Systems Architecture. The first thing to remember, the mission systems architecture of the X-47B represents an intricate network of advanced technologies working in perfect harmony. The US Navy drone combines sophisticated sensor arrays with powerful processing capabilities to execute complex missions autonomously. The X-47B is equipped with a sophisticated array of advanced sensors designed to provide comprehensive situational awareness. These sensors include electro-optical and infrared imaging systems, which enable high-resolution visual and thermal surveillance. Additionally, the aircraft features synthetic aperture radar with inverse capabilities, allowing for detailed radar imaging and the ability to detect objects with exceptional clarity. The ground moving target indicator enhances its ability to track moving targets on the ground, while electronic support measures aid in identifying and countering potential threats. The inclusion of a maritime moving target indicator further bolsters its effectiveness in naval environments, ensuring the X-47B can detect and track moving targets at sea with precision. Coupled with these primary sensors, the aircraft exchanges positioning data with carrier vessels through high-speed data links at a rate of 100 times per second. This remarkable precision enables the X-47B to maintain exact positioning relative to moving carriers, essential for successful operations in various weather conditions. Important to realize that the X-47B's data processing system transforms complex human operations into digital instructions that the autonomous system can understand and execute. The processing architecture of the X-47B is designed to support a wide range of critical functions and capabilities. It ensures real-time navigation through continuous updates from GPS and positioning systems, allowing the aircraft to maintain precise control throughout its mission. For mission planning, the system autonomously optimizes routes to ensure efficiency and effectiveness. In terms of threat assessment, it analyzes electronic warfare data to detect and counter potential risks. The system also enhances target recognition through multi-sensor fusion processing, combining inputs from various sensors to accurately identify and track targets. This integrated architecture enables the X-47B to operate with a high degree of autonomy and precision across diverse mission scenarios. In essence, this sophisticated system processes information from multiple sources to support intelligence, surveillance, and reconnaissance missions. The aircraft serves as a crucial ISR node, utilizing combat network technology to provide tactical advantages to carrier strike groups in various scenarios. The X-47B features a full-sized weapons bay designed to accommodate existing missile systems. In 2016, the Navy modified the aircraft's role to focus on reconnaissance and aerial refueling while maintaining limited strike capabilities. The total program cost reached approximately $813 million by January 2012. The weapons interface system of the X-47B showcases impressive versatility by seamlessly integrating with existing naval aviation platforms, ensuring compatibility with a range of systems. It is designed to coordinate effectively with manned aircraft, facilitating smooth communication and operational collaboration. This capability supports the execution of precision strikes, enabling highly accurate and efficient targeting. Additionally, the system enhances situational awareness for F-18 pilots, providing them with valuable information to improve decision-making and overall mission effectiveness. The aircraft's ability to operate as a data relay and target designator improves the effectiveness of crewed aircraft operations. Through sophisticated sensors and artificial intelligence, the unmanned combat air system gathers real-time intelligence, ensuring naval forces maintain tactical superiority before launching from carrier decks. The X-47B completed its first autonomous aerial refueling demonstration in April 2015, receiving over 4,000 pounds of fuel using the Navy's probe and method. This achievement utilized a government-designed refueling interface system aboard the tanker, with the aircraft autonomously maneuvering its fixed refueling probe into the tanker's drogue. Manufacturing challenges. Manufacturing the X-47B presented unique challenges that pushed the boundaries of aerospace engineering. Primarily, the program demanded innovative solutions for producing a carrier-capable, unmanned aircraft that could withstand harsh maritime conditions. The production process of the X-47B focused on developing durable composite structures designed to endure the harsh conditions of corrosive saltwater environments. To meet these demanding requirements, the manufacturing team created specialized materials that served multiple purposes. Carbon fiber composites were used to ensure the aircraft's structural integrity, providing strength and durability. Anti-corrosion coatings were applied to protect the aircraft from the corrosive effects of the maritime environment, ensuring long-lasting performance. Radar-absorbing materials were integrated into the design to enhance the aircraft's stealth capability, minimizing its radar signature. Finally, thermal protection systems were incorporated to manage engine heat, preventing overheating and maintaining optimal performance during high-stress operations. Notably, the wing structure underwent rigorous testing, demonstrating exceptional strength by withstanding loads 22% above Navy requirements. The manufacturing process incorporated advanced composite layering techniques, utilizing multiple layers of specialized materials to achieve the required structural properties. The assembly process introduced groundbreaking solutions, notably in hydraulic systems integration. Eaton Hydraulics Group developed sophisticated components, including engine-driven hydraulic pumps, advanced reservoir systems, specialized selector valves, and custom-designed hoses with Rheinlock tube fitting technology. Indeed, the assembly process required extensive testing through an Ironbird test rig at Northrop Grumman's Unmanned Systems Center. This testing phase revealed critical issues with pressure pulsations in hydraulic systems, leading to innovative solutions through attenuator implementation. The quality assurance process for the X-47B implemented rigorous protocols to ensure the aircraft's readiness for carrier operations. Through extensive testing phases, the drone achieved exceptional reliability, meeting and often surpassing the demanding standards of naval aviation. The quality control efforts were centered around validating the structural integrity of the aircraft, including wing load testing that exceeded Navy requirements and conducting fatigue analysis on critical components to assess long-term durability. Environmental stress testing further ensured the X-47B could withstand the harsh conditions of maritime operations. The systems integration process was also carefully verified, which involved validating the performance of hydraulic systems and testing the compatibility of electronic systems. Additionally, the aircraft underwent corrosion resistance certification to ensure it could endure the corrosive effects of saltwater exposure without compromising its operational capabilities. As a result of these rigorous quality measures, the X-47B demonstrated exceptional reliability during carrier operations. The program's initial contract value of $635.80 million expanded to $813.0 million by January 2012, reflecting the comprehensive nature of development and testing requirements. In addition to standard quality protocols, engineers developed specialized testing procedures for the hydraulic systems. The Hydraulic System Frequency Resonance program enabled high-fidelity testing of critical components. This innovative approach allowed engineers to identify and resolve performance issues early in the development cycle. Considering that maritime operations posed unique challenges, the manufacturing process incorporated specialized de-icing and lightning protection systems. The quality control program validated these protective measures through accelerated environmental testing, ensuring reliable performance in diverse operational conditions. The manufacturing facility at Air Force Plant 42 in Palmdale, California, served as the primary production site. This location provided the specialized infrastructure needed for assembling such a sophisticated aircraft. The facility's capabilities supported the production of 2 demonstration vehicles, which remained in flying condition rather than being converted to museum exhibits. Performance metrics and testing. Rigorous testing programs validated the X-47B's groundbreaking capabilities across multiple operational scenarios. Throughout its development, the unmanned aircraft underwent comprehensive evaluation phases that established new benchmarks in autonomous aviation. The expansion of the X-47B's flight envelope began at Edwards Air Force Base, where the aircraft showcased exceptional performance capabilities. During this phase, the X-47B reached altitudes exceeding 15,000 feet and successfully performed a range of maneuvers crucial for carrier operations. The testing program covered several key areas, including cruise configuration flights, high-intensity electromagnetic interference testing, precision approach procedures, and autonomous wave-off functions. The first X-47B demonstrator made its maiden flight on February 4, 2011, at Edwards Air Force Base. Remarkably, the aircraft performed so reliably that the preliminary testing phase concluded after only 16 flights, far fewer than the original plan of 50 tests. The carrier qualification testing for the U.S. Navy's X-47B drone delivered outstanding results across various vessels. During this phase, the aircraft completed a series of crucial maneuvers, including 8 catapult launches, 30 touch-and-go landings, and 7 arrested landings. The X-47B demonstrated exceptional precision during carrier operations, culminating in a significant milestone on July 10, 2013, when it performed its first arrest landing on the USS George H.W. Bush. Throughout the testing, the aircraft exhibited remarkable accuracy, consistently landing within just 7 centimeters of its target during carrier landings. The X-47B's operational reliability exceeded expectations across various test scenarios. Between August 17 to 24, the aircraft conducted 5 catapult launches, 4 arrestments, 9 touch-and-go landings, and nighttime deck handling evaluations. Ultimately, the aircraft demonstrated its ability to maintain 90-second launch and recovery intervals alongside manned aircraft. This achievement proved crucial for integration with carrier operations. The testing program culminated in several historic milestones. In April 2015, the X-47B completed the first autonomous aerial refueling demonstration, receiving 1,815 kilograms of fuel from a Boeing 707 Omega tanker. This achievement solidified its capability to perform standard missions alongside manned aircraft. The aircraft's reliability was further validated through its navigation system performance. When one of 3 navigational subsystems experienced a malfunction, the remaining 2 systems identified the anomaly and initiated appropriate contingency procedures. This demonstrated the robustness of the aircraft's autonomous decision-making capabilities. Flight testing expanded to include cooperative launches and recoveries with FA-18 aircraft. The X-47B operated approach speeds of 120 miles per hour at pattern altitudes of 1,200 feet. Mission operators maintained full control during multiple planned precision approaches to the carrier. The extensive testing program included a variety of critical assessments. It began with shore-based catapult launches at Naval Air Station Patchen River, followed by carrier qualification testing aboard the USS Harry S. Truman. The program also involved advanced integration testing with manned aircraft to ensure seamless coordination between the systems. Additionally, the testing phase included validation of the aircraft's ability to operate effectively during night missions, further proving its readiness for diverse operational conditions. By August 2014, the testing phase concluded with the X-47B achieving all primary demonstration objectives. The aircraft completed 5 catapult launches, 4 arrestments, and 9 touch and go landings during its final test period. These achievements established the foundation for future carrier-based unmanned aircraft development. The testing program's success led to the Navy's decision to continue X-47B flight operations through 2014 and beyond. The aircraft's consistent performance and reliability throughout the testing phase demonstrated its readiness for operational integration with carrier air wings. The X-47B is a groundbreaking achievement in military aviation, showcasing remarkable capabilities in autonomous flight and carrier operations. With its innovative flying wing design and advanced stealth features, it has redefined unmanned aerial systems. The aircraft's success in autonomous aerial refueling, precise carrier landings, and seamless deck operations proves its engineering excellence. From cutting-edge materials and manufacturing innovations to rigorous testing, the X-47B has set new standards in naval aviation. Its $2 billion program has paved the way for future unmanned combat air systems, strengthening naval aviation for years to come. What do you think the future holds for autonomous military drones? Drop your thoughts in the comments below. If you find this video interesting, please like and subscribe to the channel. Thank you for watching the video.